Imagine lining up every Duracell battery made in a single year. You'd wrap around the Earth more than twice. That's a mind-bending number of copper tops powering everything from remotes to smoke detectors. But how does Duracell actually pull off this insane pace of 10 billion batteries a year? Think about how invisible batteries are to us. They're everywhere. The remote you throw at the couch cushions, the flashlight you only remember when the power goes out, the smoke detector that suddenly starts chirping at 2 a.m. and makes you question every decision in life. We take them for granted until the moment they die, and then, suddenly, it's a crisis. Duracell has become the name people trust in those exact moments, partly because of that iconic copper top design, but mostly because for decades they've built a reputation for reliability. And yet, their story doesn't start with your TV remote or your kid's toy. It begins nearly a century ago and in a completely different world. Back in the 1920s, Samuel Rubin wasn't dreaming about AAs and AOAs sitting in blister packs. He was a scientist focused on developing better battery cells for specialized equipment. Alongside businessman Philip Rogers Mallory, they formed a company that at first made mercury batteries. And while mercury doesn't sound like the most user-friendly ingredient today, back then it was a breakthrough. These batteries became especially valuable during World War II, when the military needed cells that wouldn't give up in tropical humidity. The devices they powered had to keep running, no matter the climate, no matter the conditions. That reliability in the middle of war zones built the foundation for what would later become Duracell. The real shift happened in the 1960s. The company pivoted toward alkaline batteries, the kind you and I use every single day, and they needed a name that captured the promise: durable plus cell, Duracell. It was simple, but it was a promise. These little powerhouses would last longer than the competition. That brand identity solidified even further in 1973 when they rolled out the copper top design. Suddenly, you didn't even need to read the label to know it was a Duracell. It was sitting there in every grocery aisle, shiny and confident. That little bit of metal wasn't just branding, it was genius marketing that burned the image into consumers' heads. Ownership of the company bounced around over the years. First Kraft, then Gillette, then Procter & Gamble. Today, it's owned by Berkshire Hathaway. Yes, that means Warren Buffett, arguably the most famous investor alive, controls the batteries in your remote. You can almost picture him smiling every time you buy a 4-pack, knowing that even in the age of smartphones and high-tech gadgets, the humble AA battery still makes the world go round. So what actually makes up a Duracell battery? On paper, the recipe sounds like a science experiment that you'd probably fail in high school chemistry. Zinc, manganese dioxide, potassium hydroxide, graphite. Wrap that in steel, cap it with brass. Done. Except, of course, it's not nearly that simple. Zinc acts as the anode or negative terminal. Manganese dioxide is the cathode, the positive terminal. Potassium hydroxide is the electrolyte, the part that lets ions move back and forth. The outer casing is nickel-plated steel, tough enough to handle the chemical reactions inside while keeping everything sealed away. And that copper top? It's not just decoration. It's a nickel-plated brass cap designed to help conduct electricity cleanly into your device. Now, lots of companies could throw these materials together and call it a battery. But Duracell's entire reputation rests on the fact that they don't just toss stuff in a mixer and hope for the best. They use proprietary additives, precise formulas, and rigorous quality control that ensures consistency across billions of units. Every batch of raw materials gets tested before it even enters the production line. If the zinc isn't pure enough, if the manganese dioxide isn't up to spec, it doesn't make the cut. That's how they guarantee that whether you're buying a Duracell in Georgia, or in Belgium, or in China, it'll perform exactly as expected. And speaking of Georgia, Duracell's flagship factory in LaGrange is basically a cathedral of battery making. Imagine a production line moving so fast it pumps out 300 batteries every minute at each assembly station. Multiply that by multiple lines and you're looking at over 3,500 finished units per minute. It's like popcorn in the microwave, except instead of a snack, you get enough power to keep half the gadgets in your house alive. The process starts with preparing the cathode mix, which is basically a carefully engineered cocktail of manganese dioxide, carbon, and secret ingredients Duracell doesn't talk about. This mix is pressed into little rings or sleeves that form the outer portion of the battery's core. Meanwhile, zinc powder is prepared with its own additives to make it more conductive and less prone to corrosion. These two powerhouses, the anode and cathode, are kept apart by a separator, a thin paper-like material that lets ions pass but stops the two from directly touching. Think of it like putting up walls between roommates who really shouldn't be living together but still need to share the Wi-Fi. The steel casing, which will become the body of the battery, is formed and nickel-plated to fight corrosion. The copper tops are stamped out of brass sheets, polished, and set aside for later assembly. Then comes the moment when everything comes together. The cathode rings slide into the casing. The separator goes in next. The zinc mixture fills the center. A carefully measured amount of potassium hydroxide electrolyte is added. And finally, the copper top is attached, along with a plastic insulating washer to make sure the positive and negative sides don't accidentally connect. Sealing the unit is a critical step. Too loose and the battery could leak. Too tight and internal pressure could cause problems. Duracell has spent decades perfecting this process. Once sealed, the battery moves straight into testing. Unlike some rechargeable batteries that need forming, alkaline cells like Duracell's are ready to go as soon as they're built. But that doesn't mean they skip testing. Oh no. Every single one faces a gauntlet of checks that would make a Navy SEAL sweat. High-speed cameras look for visual defects. Automated systems measure voltage, resistance, and capacity. Samples from every batch are tortured with stress tests, extreme temperatures, accelerated aging, and leakage tests that simulate the worst conditions you could throw at them. One of Duracell's most important promises is that their batteries won't leak and destroy your expensive gadgets. That's why they put every unit through conditions harsher than anything you'd see in normal use. It's like training for the Olympics, just so the battery can live a quiet life inside your garage door opener. Packaging is another area where Duracell has flexed its muscles over the years. When they rolled out Duralock technology, promising a 10-year shelf life, it wasn't just a marketing slogan, it was a legit shift in how batteries were preserved. By sealing them more effectively, Duracell made it possible for people to toss a pack in a drawer and still expect it to work a decade later. That's not just chemistry doing the heavy lifting, it's smart packaging design working hand in hand with the product itself. And they didn't stop there. They added little power check features so you can actually test a battery before you put it in your device. It's like a sneak preview that saves you from the classic, "Is it the remote or the battery that's dead?" guessing game. For smaller coin-style batteries, Duracell went one step further and created child-resistant packaging. Anyone who's ever dealt with toddlers knows they'll try to put just about anything in their mouth, so making sure those shiny little discs are locked behind tough blister packs is a lifesaver. Literally. Sustainability plays a growing role too, and Duracell has been quietly reshaping how its products reach us. Over the years, they've cut down on excess packaging, ditched unnecessary plastic windows, shrunk the overall pack sizes, and boosted the amount of recycled material they use. Their philosophy is straightforward. When you're selling billions of packs every single year, even small changes add up to massive differences. Less plastic, less cardboard, less waste. It's a ripple effect that becomes a wave when you're operating at Duracell's scale. And it's not just what you see on the store shelf. Inside their factories, like the flagship plant in Georgia, they've taken sustainability just as seriously. That facility has committed to sending zero waste to landfills, which means everything is either reused, recycled, or repurposed. They've also slashed water usage by millions of gallons annually through efficiency upgrades. For a company that runs production lines day and night, cutting that much resource use is no small feat. These shifts might not be as flashy as the copper top design, but they matter, and they show that even in the world of disposable batteries, there's room for responsibility. Duracell isn't stopping at alkaline either. The copper top may be their superstar, but behind the scenes, they've been steadily building a lineup that covers just about every corner of modern life. They've got rechargeable batteries for people who hate running to the store every other week, ultra-tiny hearing aid batteries that pack a surprising punch, but sleek power banks that keep your phone alive when you're traveling, and of course, the Optimum line. That one's built for the gadgets that seem to inhale energy, high-drain devices like game controllers, motorized toys, and fancy flashlights, or for anyone who just wants their batteries to hang in there a little longer before giving up. What makes it impressive is how far the chemistry itself has come. The stuff inside today's Duracell cells is light years ahead of what you would have bought off the shelf even 10 years ago. They've squeezed out more power, stretched the shelf life, and made the whole package more reliable, all without changing the size. So your AA battery still looks like the same old AA battery, but it's been hitting the scientific gym behind the scenes. It's a little like upgrading your phone every few years, except your batteries keep evolving without forcing you to learn a new charging cable. They just keep slipping into the same remote slot, the same flashlight, the same controller, only now with extra endurance tucked inside. Now you might be thinking, this is all great, but it's still just a battery. Does it really matter? The answer is yes. In disaster zones, when the grid goes down, batteries keep radios alive, flashlights shining, and medical devices working. Duracell even has a rapid response program that delivers free batteries to areas hit by natural disasters. In developing regions where power grids are unreliable or non-existent, a simple battery might mean a child can study after dark, or a family can run a radio. That long shelf life suddenly isn't just a marketing feature, it's a lifeline. Economically, Duracell's global empire supports thousands of jobs directly and many more through supply chains. The factories not only power your gadgets, they power local communities. And that's part of why Duracell has managed to stay not just relevant, but dominant in an age when technology is constantly shifting. From its unlikely beginnings in the 1920s through military breakthroughs in the 40s to consumer dominance in the 70s, and now as a global powerhouse under Berkshire Hathaway, Duracell has built its name on one simple promise: reliable power. Billions of times a year, that promise gets fulfilled in devices all over the world. So the next time you pop a copper top into a smoke detector or shove a couple into a game controller, remember the journey it's been on. From carefully tested raw materials, through high-speed assembly lines, brutal quality control, and into packaging designed to keep it fresh for years. It's more than just a little cylinder of chemicals. It's 100 years of innovation squeezed into the palm of your hand. And if you enjoyed getting an inside look at how something so small makes such a big impact, the cables that charge phones, sync data, and keep devices running, they seem simple. But behind every strong, flexible USB cable is a fascinating process where ultra-fine copper, molten plastic, weaving machines, and precision tools come together in perfect sync. Right from the raw copper wires to the final bend test that breaks them, there's a whole world hiding inside every wire. It all begins with copper. Not just one strand, but 50 razor-thin copper threads that come together to form a single strong conductor. They're twisted or stranded into one bundle. It's not just about strength, though that matters, it's about flexibility. A single thick wire would snap with repeated bending. But twist 50 tiny threads, and you get the strength of a rope with the bendiness of a vine. This stranding process is a dance of precision, where every copper strand must flow in perfect alignment. And the machine that handles this, it doesn't pause, doesn't blink, just feeds the wires in, spins them with rhythmic consistency, and sends out perfectly stranded cores. Now, stranded wires alone aren't enough. These tiny conductors have to be shielded from the chaos of the world: electromagnetic interference, temperature shifts, friction. That's where shielding steps in. A wrap of aluminum foil comes around the stranded core, turning the cable into a mini fortress. This isn't ordinary foil either. It's ultra-thin, lightweight, but incredibly effective at bouncing off stray signals. Wi-Fi routers, Bluetooth devices, electrical noise, all of it blocked out. This shield ensures that when data flows, it flows clean and fast. Inside a typical USB cable, there are usually 4 internal wires, each one insulated, color-coded, and ready to transmit power and data. But before they can be bundled into the final cable, something clever happens. Talcum powder, yeah, baby powder, is dusted between these wires. Why? Because when the plastic sheath is extruded around them, they shouldn't stick together. Talcum keeps everything smooth, letting the wires move slightly within the sheath without damaging each other over time. This tiny step makes a massive difference. Without talcum, the plastic sheath could cling to the wires too tightly, causing stress points that wear down over time. Even a millimeter of movement can protect a cable from breaking internally. And it's not just sprinkled on randomly, it's applied with specialized dispensers that coat each wire evenly, ensuring no clumps or bare spots. It's almost invisible when applied, but its presence is crucial. This powder layer acts like a silent guardian, reducing friction, absorbing micro vibrations, and even helping during the cooling phase after extrusion. It also plays a role in how the cable handles long-term use. When the cable bends, twists, or stretches, the internal wires can glide subtly inside the sheath instead of locking up. This gliding motion is what extends the life of the cable, especially under daily stress like being coiled, pulled from pockets, or jammed behind desks. The cable remains flexible, not because the outer sheath is soft, but because the inside isn't fighting against itself. Even during testing, cables with properly applied talcum show fewer failures in the flexibility and stress tests. It's such a small addition, but it's like adding lube to an engine. The system just works better. It's another example of how the tiniest details in manufacturing are often the most important. Most users will never know it's there, but every time a cable survives another bend, another twist, another accidental yank, talcum deserves some of the credit. And then comes the extrusion. Picture a hot pressurized machine forcing molten plastic over the wire core, like squeezing toothpaste onto a brush. The sheath forms instantly, but it's soft at first, so it hits a cooling tank right after, where cold water helps it solidify into that familiar, flexible outer layer. Once it's cooled, a quick check ensures the diameter is just right. Too thick, and it becomes clunky. Too thin, and it risks breaking. Consistency here means quality later. At this point, the cable's starting to look familiar, but it's still missing one of the most critical layers: the braid. Now this is the part that's honestly mesmerizing to watch. A USB data cable braiding machine comes to life like a maypole dance, spindles spinning, threads flying as nylon or polyester fibers wrap around the cable with hypnotic speed and precision. It's not just for looks, though yes, the nylon does come in a rainbow of colors and gives cables that textured premium feel. But it's also about strength. This braided layer massively improves wear resistance. Drag it across a desk 1,000 times, stuff it into backpacks, twist it in weird angles. That nylon shell can take it. On some machines, up to 48 carriers spin at once, moving at speeds as high as 360 RPM. Creating an intricate woven layer in seconds. And the best part? It's all automated. Just feed in the cable, set the bobbins, and watch the machine perform its dance. What's even cooler is that this braided shell isn't just about toughness. It adds electromagnetic shielding too, especially when woven with tin-plated copper or aluminum magnesium wire. In some cases, the shielding efficiency reaches 60 decibels at 1 gigahertz. Which means it's blocking out a ton of interference. That's not something you see, but it's the reason why your cable works reliably in noisy environments. Of course, machines do a lot, but not everything. Human hands still play a role, and a crucial one. There's finesse needed in certain stages that even the most advanced robot arm can't replicate. Not yet anyway. For example, when it's time to attach the USB connectors, people often prep the cable ends manually. The outer sheath is stripped, the wires exposed and trimmed with precision, then comes the soldering. USB Type-A, the classic rectangular connector, and USB Type-C. Flux is applied to ensure strong oxidation-free joints, and the heat must be just right. Too hot, and you'll scorch the wire. Too cool, and the solder won't bond correctly. That delicate balance is something no machine can fully feel. It takes human intuition. Some factories have semi-automated soldering stations where machines assist with the repetitive motions, but the prep work and final inspections are still handled by technicians. Technicians often check each unit by giving a firm tug after assembly, verifying the joint's integrity without needing software or sensors. So while machines speed things up and keep the process efficient, the hands-on work adds the reliability. Every cable is checked for visual flaws, uneven sheaths, misaligned connectors, discoloration, or anything that might hint at deeper issues. These aren't just cosmetic checks. A small flaw on the outside can mean a big problem inside, so this final pass ensures that every cable not only works, it looks like it should. Now, here's where things get really serious. Ever wonder how cables claim to survive thousands of bends? There's an actual robot that tests that. It bends the cable again and again in tight angles, simulating the way users twist and turn them in real life. This machine does the same movement over 10,000 times. Eventually, even the strongest cable will snap, but the goal is to find out when. That breaking point tells manufacturers whether their materials and designs are truly holding up to real-world use. The test rig looks simple at first, just a robotic arm moving rhythmically, but it's doing something vital. Each bend happens at a precise angle with measured force, replicating the common abuse a cable takes, being yanked off desks, coiled and uncoiled, twisted while charging in bed, or bent at weird angles inside backpacks. Over time, these small motions can cause internal fractures, even when the outer sheath looks perfectly fine. During this endurance test, high-speed sensors track the resistance and continuity of the cable in real time. The moment even one internal wire breaks or loses connection, the test stops. Engineers then pull that cable apart and inspect where and how it failed. Did the copper strand snap? Did the solder give out? Or did the plastic stretch and shift too much? These failures become lessons, directly influencing future designs. Some cables are tested in batches of hundreds. Results are logged, charted, and compared across materials, manufacturing variations, and even different braiding techniques. It's not just about pass or fail, it's about understanding durability in the harshest conditions. Brands that advertise higher bend counts are often those that invest heavily in this type of stress testing. What's even more interesting is how certain reinforcements, like braided nylon and flexible strain relief designs, consistently extend cable lifespan. In some premium cables, the breaking point doesn't come until after 20,000 or even 30,000 bends, nearly triple the average. Those stats aren't just marketing fluff, they're born from months of physical punishment in testing labs. And it's not just one bend axis being tested. Some setups test side-to-side motion, some test vertical strain, and others rotate the connector while bending the cable, which is a common movement when devices shift during charging. All of this helps build a realistic picture of how a cable survives in hands, pockets, and under desks. At the end of the day, these repetitive motions separate cables that just look good from those that actually perform. That little sticker saying 10,000 bend lifespan? It's backed by relentless testing, mechanical arms, and teams of engineers watching every snap and shift. It's the kind of behind-the-scenes torture that makes sure the cable you grab in a rush doesn't fail when it matters most. Cables that survive longer get rated higher. Some of the best can handle over 30,000 bends. Others start failing around 10,000. Either way, this test separates the strong from the weak and shows whether the braided nylon, the stranded copper, the soldered joints, and the injected casing all do their job as one solid unit. And in the end, it's not just about surviving, it's about delivering. Some cables, like high-performance USB-C models, offer fast charging capabilities up to 66 watts. That's enough to power tablets, laptops, even some small appliances. And to hit that kind of power, everything has to be built to spec. From the wire gauge to the shielding to the soldering and connector type, every part matters. That's the full journey. From the raw copper strands all the way to the final bend test and performance rating, it's a mix of science, engineering, craftsmanship, and high-speed machines working in harmony. And even though a USB cable might seem small, the technology inside is anything but. So the next time one of those cables powers up a phone, syncs your files, or charges a smartwatch, that's not just a wire. It's a result of meticulous design, careful testing, and some truly mesmerizing machines spinning, soldering, and shaping the strongest wire that lives in your pocket. Like this deep dive, it all begins with something most people never think twice about: a roll of metal. Not just any metal, aluminum foil, but not the kind you'd use in your kitchen. This foil is destined to become part of the powerful little device that sits quietly in backpacks, pockets, or desk drawers, waiting for the moment a phone hits 1%. This is the positive electrode in a lithium battery, the very heart of a power bank. Before anything takes shape, the aluminum foil is carefully coated. It's not just dipped in any liquid. This mixture is engineered to the molecule. It includes active materials like ternary compounds and lithium manganese oxide. Conductive agents help electrons move freely, binders hold the structure together, and solvents keep everything just the right consistency. The mixture is spread evenly across the aluminum using a precision coating machine, forming a sticky black film. Once coated, the foil goes through a drying process where all that solvent evaporates, leaving behind a perfectly smooth layer of electrode material. It's during this drying phase that the real transformation begins. The same coating process happens for the negative electrode too, except copper foil is used instead of aluminum. And that slight change in material makes a massive difference when it comes to battery chemistry. After drying, there's no time to waste. The coated electrodes are passed through a roll press. The goal here is to squeeze the material thinner and denser. That not only saves space, but ensures a consistent structure, which is crucial for performance. A properly pressed surface reflects light, almost like a mirror. That shiny finish? It's a sign the electrode is ready for the next phase. Now the material is trimmed, or what they call slitting. Picture these wide-coated sheets being sliced into narrow, clean strips, each one ready to be turned into the inner workings of a battery. The edges are flawless, the waste is vacuumed up and recycled. It's clean, efficient, and surprisingly satisfying to watch. Once the slitting is done, the next step is tabbing. Here, small metal tabs are welded onto both the positive and negative electrodes. Aluminum tabs for the positive side, nickel tabs for the negative. These tabs will eventually be the connection points for the power bank's circuit board. But they're not just tacked on. Each weld has to meet specific tensile strength standards. If it's too weak, the battery won't survive assembly. If it's too strong, it risks damaging the thin electrode materials. It's all about balance. The machines performing these welds are tuned to microsecond precision, delivering just enough energy to create a bond without burning through the material. In a single shift, thousands of tab welds are performed, and each one must be flawless. Sensors monitor the current, pressure, and temperature in real time, flagging even the smallest anomaly. Sometimes a tab weld may appear perfect on the surface, but internal resistance tells another story. That's why additional electrical tests are often run after this step. Tabbing also sets the stage for how well the battery integrates into the larger power system. If the connection points are even slightly misaligned, it can cause serious issues during assembly. Operators often work under magnifiers, using cameras and screens to guide placement down to the millimeter. There's a visual rhythm to this stage. Clean, consistent welds lined up like stitches on fabric. Each spark from the welder is a tiny burst of precision engineering. Depending on the battery format, the tab length and position might change, but the core principle remains the same: strength without compromise. Sometimes the tabs are folded or bent to prepare for the next stage, and that bend needs to be perfect. Too sharp and it could crack under stress. Too loose and it might not fit properly into the final pack. In high-capacity designs, dual-tab configurations are sometimes used to distribute current more evenly. That adds another layer of complexity, but also improves performance. Engineers often revisit the tabbing stage when optimizing for efficiency or improving battery longevity. Even the tab material itself is carefully selected for conductivity, durability, and cost. It's a small part of the battery, but a vital one. In many ways, the tabs are the silent heroes of energy transfer, and once this precise dance of welding and alignment is done, the battery is finally ready to be shaped into the energy core that powers a modern device. With tabbing completed, it's time to build the core of the battery. Using an automatic winding machine, the positive and negative electrodes are carefully wound together with a separator sheet sandwiched in between. The separator does exactly what it sounds like. It keeps the two electrodes from touching each other directly. If they ever did, it could lead to a short circuit, or worse, a fire. Winding this way ensures compact, high-capacity cells that are safe and reliable. But winding isn't where the checks stop. The wound battery cores go through X-ray inspection. And yes, that means the inside is scanned like luggage at an airport. This step ensures the layers are perfectly aligned and free of defects. Any core that doesn't meet the standard is removed before it causes problems later. Once the internal structure is cleared, the battery core gets its outer layer. It's inserted into an aluminum plastic film casing. A heated copper mold seals the edges to keep everything airtight. This film isn't just for looks. It's flexible, strong, and lightweight. Perfect for the slim, modern design expected in portable tech. But the battery isn't alive yet, not until it's baked, literally. These cells are placed in a high-temperature vacuum environment. The goal here is to remove every last trace of moisture from inside the cell. Even microscopic droplets can mess with performance or create long-term safety risks. After baking, it's finally time for one of the most important steps: electrolyte injection. The electrolyte is a special liquid that allows lithium ions to move between the electrodes. Too much or too little, and the battery won't work as intended. So every battery is weighed before and after the injection. It's not a guess, it's science. Only the correct amount will ensure proper function. The electrolyte acts like the bloodstream of the battery, enabling the essential chemical reactions that store and release energy. But it's also highly sensitive. The environment has to be perfectly controlled. Humidity levels, temperature, even air quality, all of it matters. During injection, the battery cell is placed in a sealed chamber to minimize exposure to air because the electrolyte can react negatively with moisture. It's why even a tiny air leak can ruin a cell. The machinery used for injection has to be incredibly precise. We're talking about fractions of a gram here. Micro adjustments to ensure just the right balance. After the injection, each cell is immediately reweighed to confirm the added volume. If the weight's off by even a fraction, the cell is flagged for review. The process isn't rushed. The goal is saturation, not speed. Some manufacturers even allow a short rest period after injection, letting the liquid naturally soak into the internal layers. This helps reduce trapped air and ensures better contact with the electrodes. The chemistry inside is delicate, and even distribution is key. Uneven electrolyte levels can cause performance inconsistencies or premature failure. The liquid itself varies depending on battery type, but it usually includes lithium salts and organic solvents, engineered for fast ion mobility and stability. There's a whole science around optimizing this formula for different battery uses. High-drain applications need faster ion transport, while long-life batteries need better stability. The containers used to hold the electrolyte are often nitrogen-sealed to avoid contamination, and operators wear gloves, goggles, and full suits to handle it safely. Even a small spill can be hazardous. Once inside the cell, the electrolyte doesn't just sit there. It becomes part of the chemical symphony. It must fill every crevice between the tightly wound electrodes, acting as a medium that makes the battery come alive. This one step, so quick in real time, can determine how well a battery performs for months or even years. That's why it's treated with the same seriousness as a launch countdown. When done right, the cell is fully charged, not just with liquid, but with potential. Once the electrolyte is in, the battery enters its aging phase. No, it doesn't mean sitting on a shelf and collecting dust. It's placed in a controlled high-temperature environment to allow the electrolyte to fully soak into the internal materials. This step helps improve the long-term performance and stability of the battery. Next up is formation. This is when the battery is charged for the very first time, and that first charge is crucial. During formation, a stable SEI layer forms on the electrodes. This layer acts like a shield, protecting the battery from degradation while allowing ions to pass through during charging and discharging. Without this step, a battery wouldn't last very long. Before final assembly, there's a final gas extraction step using a vacuum. Any residual gases are pulled out of the cell to ensure nothing contaminates the battery over time. After that, the battery is trimmed, removing excess material around the edges. This ensures the battery is exactly the right size to fit into a power bank. But performance matters most. So each cell goes through capacity testing. They're charged and discharged to measure how much power they actually hold. Cells are grouped by their capacity levels to ensure consistent performance in the final product. If one cell performs worse than the others, it's removed. Only the best make it through. Next comes the OCV, or Open Circuit Voltage Test. This checks the self-discharge rate. Batteries are left untouched for a set period, and the voltage drop is measured. A healthy cell will hold its charge. If it doesn't, it's flagged and pulled from production. At this point, you'd think the hard part is over, but the real show is just about to start. Now it's time to assemble the power bank itself. Inside the Blue Times facility, these cells are lined up for a final round of checks. They go through visual inspections, voltage checks, and safety validations. Then 2 or more battery cells are paired together to form a single battery pack, increasing the overall capacity of the power bank. And this is where things really start to spark, literally. Spot welding connects the cells using nickel strips. These high-speed welds use intense heat and pressure to fuse the metal together. It's fast, loud, and dramatic, especially when sparks fly, but it's all controlled with incredible precision. These connections must handle both energy transfer and mechanical stress. Once the cells are connected, the brains are added. That means installing the protection circuit, also known as the BMS or Battery Management System. This tiny circuit ensures safety by monitoring temperature, voltage, and current flow. It's what keeps the power bank from overcharging, short-circuiting, or overheating. Without this, using a power bank would be a gamble. Now that the inside is complete, the casing comes next. This isn't just snapped together. An ultrasonic welding machine seals the plastic shell shut. Using high-frequency vibrations, it melts and fuses the case without using glue or screws. The result? A seamless finish that looks clean and feels durable. And once it's sealed, there's no going back. The case isn't meant to be opened. The power bank is almost ready, but it's not official until it's tested. The final device goes through more aging tests to simulate long-term use. It's charged, discharged, dropped, and shaken. And yes, there's even a drop test where the power bank is smashed against a hard surface to make sure it won't break or malfunction under real-world conditions. Only the strongest survive. For branding, there's a laser printing process that adds the final logo or product details. It's clean, fast, and permanent. And just like that, a brand new power bank rolls off the line. Sleek, compact, and ready to charge anything from phones to tablets and beyond. Behind every power bank is a journey of chemistry, engineering, precision, and innovation. And at the center of it all is Blue Times, a company with over 18 years of experience in building smart, sustainable, and reliable energy solutions. As a leading OEM and ODM partner, Blue Times doesn't just build power banks. They engineer trust, consistency, and performance. With patented designs, rapid development cycles, and factory-grade precision, their technology helps brands stand out while delivering the power users depend on every single day. From aluminum foil to circuit boards, from baking ovens to drop tests, this process is a reminder that portable energy isn't just about convenience. It's about innovation, it's about safety, and it's about turning science into something people carry in their pockets without ever. The birth of the body where heat meets shape. Before light can exist, it needs a home. That home, the LED bulb body. It's built to be strong, heat-resistant, and light-friendly. The process begins with placing the aluminum heat sink. That's not just any piece of metal. This is a vital part of the bulb that pulls away heat, keeping things cool even when the light's been on for hours. If it weren't there, the LED chip would burn out faster than you could say eco-friendly. After the heat sink is set, the base of the bulb starts taking shape through injection molding. Picture this: molten plastic. Hot and gooey, being injected into perfectly shaped molds. In seconds, it cools and hardens into the shell that will eventually hold all the inner components. It's fast, precise, and oddly satisfying to watch. Now it's starting to look like something real, not just a blob of plastic and aluminum, but the beginning of something that will one day light up a room. The LED chip? Tiny but mighty. At the heart of every LED bulb is a tiny yellow square, the LED chip. Don't let its size fool you. This is the real light maker. It's like the engine in a car or the CPU in a computer. Small but essential. The process kicks off with surface mount technology, or SMT, where these chips are delicately placed onto circuit boards with almost inhuman precision. Machines do this part because the chips are tiny, like really tiny. Trying to place them manually would be like threading a needle while blindfolded, with chopsticks. But for all the machine magic, there's still a human touch involved. Skilled workers step into solder wires onto the direct-on-board DOB LEDPCBS. It's a careful process. Each connection matters. A single weak joint and the bulb might never shine. And then come the IC drivers, little integrated circuits that control how power flows through the bulb. These are separated, sorted, and soldered onto the LEDPCBS, again by hand. Not because machines can't do it, but because these drivers are delicate, and sometimes machines just don't have the finesse. Some LED bulbs are compact, with IC drivers so tightly packed that assembling them by hand is the only option. Add to that certain sockets like the B22, which require hand assembly because automated tools just can't handle the design. It's a blend of automation and craftsmanship that keeps the process flowing. The driver, invisible but essential. Ever wonder how a bulb handles the electricity straight from your wall outlet? That's where the driver comes in. It's the silent workhorse hidden in the base, making sure everything runs smoothly from the moment power hits the socket. Tucked away inside the bulb's foundation is a small but essential circuit board that acts like a translator in taking the high voltage alternating current, AC, that flows through household wiring and converting it into the low voltage, steady direct current, DC, that the LED chip requires to shine bright without burning out. Without this component, flipping the switch wouldn't do anything but send raw voltage to a chip that's just not built for it. The journey of the driver begins with delicate precision. First, there's the soldering. Wires must be connected to just the right points, with clean joints that won't fail or under long hours of use. It's not simply about connecting parts, it's about ensuring those connections can handle surges, dips, and constant current flow. The driver board itself is mounted with care, often by hand, especially in more compact bulb designs where machines can't easily reach. These tight configurations demand human finesse, and the workers handling this part are incredibly skilled at making sure every lead is placed perfectly. Some LED bulbs operate with external or modular IC drivers, which are small integrated chips that regulate power flow. Others go the compact route, embedding the driver directly onto the main board. Both approaches have their advantages, but what they share is the absolute need for reliability. These components have to survive thousands of on-off cycles, endure voltage fluctuations, and keep the light steady without flickering or overheating. At this point in the production line, the bulb's internals are beginning to sink. It's a small symphony of micro-components now fully assembled, from chip to board, from wires to drivers. Electricity will enter at one end, travel through carefully soldered paths, get conditioned and converted by the driver, and finally reach the LED chip in just the right form. It's the technical heartbeat of the bulb. Yet, even with all this carefully crafted tech sealed inside, the bulb isn't quite finished. It still needs protection, polish, and proof that everything works the way it should. But for now, it stands as a fully wired promise, ready to turn energy into light with a single flip of a switch. The globe covering the light. With the engine ready and the wiring in place, the next step is to protect and shape the light. That's where the PC cover comes in, the dome-like cover that gives the bulb its familiar look and helps spread the light evenly. It's more than just a finishing touch, it's the diffuser, the final frontier between raw brightness and comfortable illumination. Depending on the design, this dome might be made from either plastic or glass, and each material brings its own character to the bulb. Plastic covers dominate most production lines due to their lightweight and durability, and the way they're made is nothing short of mesmerizing. The process begins with injection molding, molten plastic heated to the perfect temperature, then shot into molds that give it that smooth, curved shape. Once cooled, the covers are crystal clear or gently frosted, depending on the desired lighting effect. In some specialized production lines, the classic charm of glass is still used. It's a slower, more delicate process involving glass blowing, shaping the red-hot material into seamless domes before letting them cool into a pristine, transparent shell. Whether glass or plastic, each dome must be flawless. Any bubbles, warps, or scratches can affect how the light disperses. When ready, these domes are moved to the assembly line, where robotic arms take over. With sharp, precise movements, the arms grip each cover, rotate it gently, and lower it onto the bulb body. The alignment is spot on, no guesswork here, and the snap into place happens in one smooth, satisfying motion. But snapping alone isn't enough when the bulb will face years of heat and pressure. That's where adhesive comes in. A tiny bead of high-performance glue is applied at the base of the cover. It's clear, strong, and built to last. It ensures the dome doesn't shift, crack, or loosen over time. Once sealed, the bulb gets one step closer to completion. This entire process happens in seconds, repeated over and over across thousands of units per hour. And the result? A perfectly shaped light diffuser that not only protects the internals, but also softens and spreads the glow into something comfortable, familiar, and pleasant. The dome isn't just functional, it's what makes the bulb instantly recognizable on store shelves, and in every room it eventually lights up. Watching this part of the process unfold feels a bit like watching high-tech ballet, a dance between heat, precision, and polish. Semi-automatic magic. Humans plus machines. Here's where things get really cool. The semi-automatic production line. It's part machine, part human, and all efficiency. Workers place the assembled PCB into the bulb base and feed it into the machine. It presses everything into place with just the right amount of force. The machine also leaves enough room for the PC cover to be added later. Spacing is everything here. Next comes the socket. Whether it's an E27 or B22 base, the socket is added and locked in. Some are screwed, some are clipped, but every one of them has to be snug. A loose socket is a safety hazard, and this process doesn't allow for mistakes. Even at this speed, with thousands of bulbs moving per hour, every single one is handled with care. The aging rack, a wall of light. Production story again. Let us know in the comments what product you'd like to see made next.